Hey everybody, this is Larry. This is us doing week 5 of the weekly premium problem, 1060, missing element in sorted array. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, or these problems, or, well, I don't know, this week's problem. Alright, so given an integer array, numbers which is sorted in ascending order, or its elements unique, and given also an integer k, return the kth missing number starting from the leftmost number of the array. What does that mean? Oh, why is the first missing number 5? The missing numbers are 5, 6. Okay, I see. It's a really awkward way of saying it. Because you don't start at 1. I think that's why I feel like it's a little awkward, because you don't start at 1, but okay, fine. Yeah, I mean, I think there are a couple of ways you can think about doing this. I think you can. I mean, this is going to be binary search, or at least the way that I'm thinking about doing it. Okay, k can be 10 to the 8. I was like, if k is small, you can actually maybe do something funky about it with respect to like walking it up or something like this. There are a number of algorithms, obviously, and even with walking, it's not that bad of an idea if you don't do it linearly, right? There's this thing called I call it repeated doubling. I think some people call it galloping or something. What's it called? Repeated doubling, galloping. I've never called it this, so I always have to. Something's gallop or something. Galloping search, but I just call it repeated doubling. So, but the idea is that basically your search length is going to be 1, 2, 4, 8, 16, ... 2 to the x, and therefore it's kind of reverse of the n over 2, ... So it's going to be linear in that case, right? In theory, depending on how you do it. But is that linear? Well, linear in the size of the thing, of the number of bits. So yeah, I'm saying this very awkwardly today, because every repeating gives you one more bit of information, which is another way of doing binary search. But in any case, yeah, what is the non-log n solution? But where n is the answer, I suppose. Wait, is it? Oh, I think maybe I cheated, or maybe I lied in general. In that, I think initially I was going to do a binary search and then kind of do it this way, but actually it's n log n, so it's even worse than n, because then you could have an n solution where you basically just walk from left to right, you count the number k's off, and it should be okay, right? You just kind of do math, and then you count a k. So yeah, so in that way, it's walking it up, right? So let's repeat. You can sort and then do a linear thing. Oh, sorry, you can binary search and do a linear thing, and then yeah, but that's gonna be n log n, and then the other thing is just walking it directly, right? Meaning that you try, it's 5, is it 6, is it 7, is it 8, or whatever, right? I think I skipped 7 for some reason. It's 5, 6, 7, 8, I don't know, whatever, right? Just one at a time. So that's going to be O of n, because you can actually skip ahead, right? You go, okay, this 2, 4, that means that there's one number in between, so we just take one number from here, and then we keep going until at the end, or between one of those numbers. So that's going to be linear. So that's actually pretty good. Can we do it in log n? I mean, I think the way to do it is going to be with... Can I do it in log n? I mean, yes, it's the short story. But that function is so... yeah. I mean, I think it's still binary search. I mean, you could do the repeat doubling thing, but I think binary search actually makes more intuitive sense, because basically the idea is just to use the index as the numbers of numbers before that are not missing, right? So almost like the inverse of what you have. Let's give it a try. it's good. I'm not gonna lie, it's a little scary in that it's very easy to make silly mistakes, but this is what we're for, right? Basically, we want to find. Let's kind of define what we binary search for first, right? We want to find the index in which the kth number is between num sub index and num sub index plus 1, or infinity, right, or whatever it is. So that's basically what we want to do. We want to make it clear because that's not the answer, right? Getting the index is not the answer. Getting the index allows us to calculate the answer if we're, just in general. So and I like writing this like that because I think I get questions about is inclusive bounds, so that when left is equal to right, then we have one element in the inclusive bound. So then music is terrible. Okay, so if good is mid, I don't know how to write this yet because I don't know what the good function is, right? So that's why the hesitation. The good function is we want to and it doesn't matter how you want to write it, right? As long as you're consistent with if the question you're asking and using that as a guideline to solve the answer, it's fine. It's just that it's kind of right. Is the kth number and you can say to the left or to the right, but I'm trying to be really precise. To the left of num sub mid, maybe, right? Let's say it's this, right? And it doesn't really matter. So if this is the case, then obviously we want to shrink right, and because if it is the kth number is to the left, then mid it cannot be the answer that answers this question because it means that it is not mid and mid minus 1. So that means that right is equal to mid minus 1, and then else left is equal to mid. And then you have to do a plus 1 to kind of cancel this out a little bit. And so that means that now the answer is between num sub left and num sub left plus 1 because left is equal to right, and that is basically the only answer left. Let's write the good function first. Maybe we're jumping around a little bit, but I think that makes it a little bit clearer. So let's say we have some index x. Let's just call it index, Larry. Okay, fine. Let's say we have some index x, right? So how many numbers? Is it log n? Maybe this isn't log n. Maybe I lied. Because we want to do this in O of 1. Oh, no. This should be fine. I think this, I thought about it, but then we don't have to. We literally, so okay, num sub index, right? What does this mean? I think that's the part that I have some ideas in my head, but I have to try to be very clear about. Because it's very, this is why I said I have a healthy respect, because it's very easy to do an off by 1 or something like this. And of course, you want to do this in all of 1 time, so you have to be, which is not that bad as long as because it's just a lot of constant operations, even if you do it in a messy way. But okay. So if the nums is 4, what does this mean? That means that how many spaces are there before this number, right? because the kth missing number is going to be the number of gaps between this number. Okay, so that means that if this is the number here at the num sub index, that's the this is total numbers. Index is the number of numbers that are taken, and this is actually not quite right. It is actually this minus num sub 0 or something like this, right? Because basically this is saying that there are 3 numbers between 1 and 4. It's not quite right. Let me think about this for a second, right? Yeah, so there are, like I said, there could be plus and minus ones, but that's the general framework that we're working with. Yeah, total count of numbers to be precise. So for example, if there's 4 and the first number is 1, that means that there are 3 numbers. Is that true? Depends how you want to phrase it. I mean, I think one thing that we can do is re-index it, but obviously that'll take linear time and that'll already be longer than log n. So we can do a impromptu re-indexing by subtracting everything in our calculation by num sub 0. So that means that we can pretend this is a 0 and this is a 3, and that means that there are 0, 1, 2, 3. We know that this number is always going to be taken, literally by the definition of this number, and 0 is going to be taken. So then you minus, 1 for the number of. I guess maybe this we can also take track of that here, but we subtract 1 for the first number. Yeah. And then the index is the number of numbers that we used. So in this same case, so 0 to 3, let's just keep it this way, right? So 0 to 3 is this number of numbers inclusive. And then the third index is going to be index plus 1 in, because that's the number of numbers that includes the current index as the number, right? So then the number, so yeah, so total is equal to this. I'm writing it out just so that maybe it's easier, and then gaps is equal to taken, right? So then now, oh sorry, total minus taken, right? So that's number of missing numbers to the left of index, right? So now, is the kth number to the left of it? Well, if the number of gaps is bigger than or equal to k, then this is to the left of it. And that's basically going to be our thing. Let's print it out real quick, just so we could kind of make sure we're okay. So we print out 0 as the first index. Yeah, that's right, because the answer is between left. Here the answer is 8, so it should be 0, 1, right? We print out 1, that's good. It is what we expect. And then here the answer is 6, which is to the right of 2, which is also what we expect. Okay, I mean, it's not definitive, obviously. You know, these cases are not going to be 100% exhaustive, but it gives us at least some confidence to at least get the right. So now the answer is between left and left plus 1. Let me make this smaller. Yeah, again, we can use this formula that we had in good. So total is equal to num sub left minus is num sub 0. Taken is equal to index plus 1, and then gaps is equal to total minus taken, just for the sake of whatever. And then now k minus equal to gaps, right? Because that's the number of missing numbers that we moved. And then it should be just return nums of left plus k plus 1, because k could be the 0th number. We're doing 0 index. I think by definition it should be good. What the? Oh, this is left. We don't use index. Well, that didn't work. Maybe I just kind of, let's write it out here. Let's do it before me. maybe I just missed one step. Okay, so we start at the left. That's good. Total is 0 numbers. Oh yeah, because it's from the left, so that means total numbers from the left. Taken is 1. So total minus taken is. Oh, did I miss the +1? Yeah, I missed the +1 in my copy and paste. In my mental copy and paste. Okay, so it's still wrong, but maybe we don't need this +1. Maybe I was wrong on this one. But yeah, gaps. So we take up k gaps. So then k and gaps we use 0 gaps to the left, which makes sense because this is the first number. So then 1 is so maybe I was wrong about the 0 index. Maybe it is just 1 index, so maybe that's why we don't need this. I thought it would be 0 index, but if there's 1 gap and k is 1, then I guess it would be on the previous. Okay, fine. Yeah, maybe I buy that. All right, so that looks okay. Let's give it a submit. Hopefully we don't make a silly mistake, and we haven't. So we have a streak going on. Yeah. So I kind of talk a lot about binary search, and people always talk about templates on my Discord, on everywhere on the interwebs, really. And hopefully this is a very step-by-step kind of engagement into binary search and how I solve it without really, like you could kind of see how my thought process is every step of the way, and none of it depends on the template. I don't ask myself if it's last true, last false, last whatever. I just ask myself, what is it that I really want every step of the way, and you're able to kind of get it. Yeah, like, and if I, like for example, you can easily change this to, what's the case is to the right, and then that changes things. And it may not even be what you think, which is just flip these two, because about how you handle the inclusiveness, right, and stuff like that. So it's actually, you just answer it differently. Like maybe we this instead or something, right? It could very well be. So you have to be very careful. But you don't have to worry about being careful. You do, but you don't have to worry about how it fits into your real templates. If you're just able to ask yourself questions every step of the way that are consistent and make sense, and this, as long as you're able to kind of define this good, then you kind of implement this by itself, and you don't even have to think about how it fits in, because that's how our modular code works. And yeah, and here allow us to kind of, because this part, now we know that here the answer is between left and left +1, then we can just calculate how many gaps gets used, and that's just a very easy formula after that, right? Easier anyway. I mean, I still got it off by 1 because I kind of misunderstood a little bit. But yeah, that's all I have for this one. Maybe a short complexity, I think I forgot. Space, we only use linear space, right? Number of variables. In terms of time, this is going to be log n. We just go from 0 to n. Logarithmically, binary search, and this is all of 1, so this is log n algorithm. That's all I have for this one. Let me know what you think. And yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.